Now let's do a problem that's harder. It's not a pure antiderivative problem. Let's make it be dy dt equals y squared minus 1. Not a pure antiderivative problem. The answer is not y cubed over 3 minus y plus c. No. Y is a function of t. You want a function of t for your answer, not a function of y. Don't integrate with respect to y. Now on Wednesday, we had Mathematica find a solution of a logistic model with d-solved value. I want to show you how to solve this equation. Though technically what I'm showing you right now is not the main subject until section 11.4. But I think it's worth showing you right now to get us warmed up for 11.4 next week. It's not a pure antiderivative problem. It does have a special name. It's called an autonomous ODE, autonomous differential equation, or ODE. ODE again stands for ordinary differential equation. What does that mean? It means the right-hand side function is independent of time. You know, in everyday language, the word autonomous kind of means independent, self-governing, like an autonomous region of some country or something. When you say it's an autonomous differential equation, you're saying the right-hand side is independent of time. It's not changing over time, so to speak, in value. It only depends on y. That has more significance for even more complicated kinds of differential equations that are in higher dimensions. It still can be solved. And we're about to solve it, though I will tell you it's not easy. The technique is called separation of variables. Solve by separation of variables. What does that mean? What are the variables? The variables are t and y. Or if you expand your horizon about variables, you could also say dy and dt are variables. How about d itself? No, d itself is not a variable. dy, dt, y, and t are all variables. You'd like to get all the y's on one side and all the t's on the other. By all the y's, I mean things involving y and things involving dy. And by all the t's, I mean things involving t and then things involving dt. How? Do our favorite trick. Pretend that's a fraction. And multiply both sides by dt to cancel the dt on the left. Wait a minute, is that allowed? Technically, it's hand-wavy math. Our favorite thing to do, right? Hand-wavy math. Magic. Poof. Can it be made rigorous? Yes, but it's too hard. I probably will make an effort to make it a little more rigorous next week sometime. But to make it fully rigorous, there's a few different approaches. There's something called non-standard analysis, which deals with infinitesimal quantities. And there's also an approach involving something called differential topology, which sounds hard, and it is hard.
Yes, differential topology is three-dimensional slope fields.
You can relate to slope fields. That's true.
That was just a while.
Yep. Slope fields do come up in differential topology. So I'm going to start by pretending I'm multiplying both sides, multiply in quotes, by dt. You can make this semi-rigorous, and again, we will next week. It doesn't really justify the actual step that we're doing so much as just justifying that you get the right answer in the end. By doing that, I have put the t on the right side. I haven't fully separated the variables yet, though, because there's still a y on the right side. Now divide both sides by y squared minus 1. And write the equation like that. This equation is essentially equivalent to this equation. They are both equivalent differential equations. And actually, these expressions, dy and dt, are in fact in differential topology, and there's another subject, differential geometry. They're called differentials as well as infinitesimals, but in different, okay, it's different names in different settings. When you see something like this, especially, well, like right now, and also in like a science or engineering class, you should start getting an itch, an urge to integrate both sides. Must integrate. Yeah, go ahead and integrate both sides. And yeah, that's usually a good idea. Question?
Is it weird to have gotten that itch a step earlier? Like,
Is it weird to do what?
to have gotten it a step earlier before you divided both sides by y?
Is it weird to have done this, or weird to write that? Is that what you're saying?
I would.
Or you'd integrate right away there.
I would integrate right away.
Well, it's not wrong to write integral signs on both sides here, but the problem is you don't know what y is as a function of t. So it's better to write the y over there. Integrating the right side's easy, t plus e. Or maybe, because I'll have to integrate the left side, I should call this C1. Do I have to call it C1? No. But it's a little less sloppy to call it C1. There'll be a C2 when I do this one. When I do some more rearranging, there'll be a C3. There will even be a C4 and a C5 in this problem. And it's the C5 that we will finally call a plane C. Still got to integrate the left side. That's the same as integrating 1 over y squared minus 1. Where have we done such integrals before? They come up on the gateway? They actually did. Though typically the bottom was factored. Is that enough of a hint for you? What technique should I use? I think I'd prefer something else. Partial fractions. Oh, partial fractions. So this is one of the main places we use partial fractions, is to solve problems like this. Another main place people use partial fractions is to solve what are called Laplace transform problems, which also come up with differential equations. Question?
Could you also rewrite the integral as y squared minus 1 negative 1 power?
You could, but I don't know that there's much reason to do that. Because it's equivalent to this, so you might as well do this. If this one up top were just a 2y, or if it were a 2y, it would actually be an easier integral to do, because then you could just do a substitution. W equals y squared minus 1. But it's not, it's a 1, so we got to deal with partial fractions. So we're trying to write this function in this form, multiply both sides by the common denominator of the left, which is y minus 1 times y plus 1. It completely cancels on the left, and you get partial cancellation on the right. A y minus 1 cancels with the first term, leaving a y plus 1. And a y plus 1 cancels with the second term, leaving a y minus 1. And you can rewrite this as leading to a system of equations for a and b, but of course it's quicker to just plug in special values for y. Oops, that's a -2 there. If y is -1, then you get 1 equals -2b, so b is -1/2. And if y is +1, You get 1 is 2a, so a must be 1/2. That's the quickest way to solve for a and b. One half over y minus 1 minus 1/2 over y plus 1, and those are easy to integrate. Plug that entire expression in there. Save a little time. I won't actually rewrite it. I'll just do the integrals. I'll get 1/2 natural log of the absolute value of y minus 1 minus 1/2 natural log of the absolute value of y plus 1 plus C2, I guess. So what do I have now? I've got that this equals this. What's my goal? I'm trying to solve the differential equation. I'm trying to figure out how y depends on t. I guess I have to set these equal to each other and solve for y. Ugh. We will do it here. It's not easy, but we can do it. I could bring the 1/2s up into the powers of these things here as a property of logarithms. To avoid that, to avoid square roots effectively, I'm going to multiply both sides by 2 first. I'm also going to imagine, well, maybe imagine subtracting C2 from both sides before I multiply both sides by 2. So I'd get a C1 minus C2, and then I multiply that by 2. Maybe I should just call that C3. Tracking with me here? I can also combine these logarithms. If I've gotten rid of the 1/2, so I've got the log of the absolute value of y minus 1 minus the log of the absolute value of y plus 1. Difference of two logs is the log of their quotient. And the ratio of two things with absolute value signs around them is the absolute value of the entire thing. So what I'm trying to say is I can write that after I've subtracted C2 from both sides and also multiplied both sides by 2. That's a property of logarithms. And on the right, I do have to have a 2 in front of the t, but effectively I can just have a C3, say. So I did a few steps there at once. You might say I did 3 things at once there. I subtracted C2 from both sides, then I multiplied both sides by 2, then I used a property of logarithms. Remember what your goal is. Your goal is to solve for y. This is good because now I can get rid of the natural log by exponentiation, right? The e and the natural log are inverse functions. They will quote unquote cancel, leaving me with the absolute value of y minus 1 over y plus 1 equaling this. And with this, I could write that as e to the C3 times e to the 2t. And maybe I should call that a C4. In other words, absolute value of y minus 1 over y plus 1 equals C4 e to the 2t. Getting closer. Boy, that absolute value sign seems like it's kind of a sticking point now. Maybe I should just get rid of it. I'd like to, for certain. Is that okay? Well, maybe if I write a C5 instead of a C4, it is. Or maybe I should just call it C now. C is, say, plus or minus C4. The C4 being e to the C3 has got to be positive. So by getting rid of the absolute value signs, I can have a new C and call it plus or minus C4 and just label it C instead of all these subscripts now. I will tell you that when some people do all this, I mean, this is hand wavy as it is. This is not super justified here, all this. I mean, it makes some sense, but it's not really rigorous math. Some people even are less rigorous and they just put a C in every spot, but they're really different C's. And that's okay as long as you get the right final answer. But if you're not careful, it can lead to mistakes. So I think it's probably good to label different C's. Getting close, getting close. Trying to solve for y. How about multiply both sides by y plus 1 now? If I multiply this by y plus 1, I get c e to the 2ty minus c e to the 2t times 1. Get all the y's on one side now. Subtract c e to the 2ty from both sides and add 1 to both sides. Oh, and I made the same mistake I made in the last class. This needs to be a plus sign here. I don't know why I made that mistake twice. I guess it was stuck in my brain. Right, I got a plus sign here because there's a plus sign there. I'm almost done. Factor out a y there. And then just divide both sides by that. So if we have not made a mistake, it appears that a general solution is y equals 1 plus c e to the 2t divided by 1 minus c e to the 2t. Now you could do various things to this to write it in other ways, but this seems pretty decent. Is it really a general solution? Remember what I said it means to be a general solution, typically at least. It means every function that looks like this is a solution. I'm not going to take the time to verify that. What would I have to do to verify it? It would be harder than verifying that first example, for sure. I'd have to substitute into the differential equation on the left-hand side and the right-hand side. With the left-hand side, that means I need to take its derivative. I'd need to use the quotient rule. Take the derivative, simplify it. With the right-hand side, it means I need to replace y with that function there. I need to square it and then subtract 1 and simplify. And see if I get the same answer both ways. We did that with the logistic model on Wednesday. Took a couple minutes. Not super easy. It's tricky. So any function like this is a solution. It should also mean any solution looks like this. That's actually not quite true here. This is a general solution. Almost. It's effectively a general solution, except it misses the solution of one initial value problem. That's by no means obvious. How do I know that? Experience. And I'm about to show you the slope field. And we will see in the slope field, if we think about it carefully, one solution that gets missed. So here we're about to look at the slope field for this autonomous differential equation. Even though the right-hand side only depends on y, I will use the f of t comma y notation. Yes, now the right-hand side only depends on y, no t's. If I plug in 1, 1 into that, I still get 1 squared minus 1 is 0, but only because y is 1, not because t is 1. T is the first coordinate, y is the second coordinate. Likewise, if I plug in 2, 1, t is 2, y is 1, I get 1 squared minus 1 is 0. If I plug in 3, 1, I get 1 squared minus 1 is 0. All those points are in the same horizontal line, not the same vertical line. The slope field has 0 slope When y is 1, the horizontal line where y is 1, a bunch of little line segments with 0 slope. Hey, if you got a bunch of little line segments on a horizontal line with 0 slope, and solutions have to follow the slope field, that must mean there are some solutions that are horizontal constant functions. Y equals 1 is one of them. There's actually a second one. This formula will find the constant function y equals 1 as a solution if c is 0. C is 0 in both of those spots. Then you get 1 over 1, which is 1 for all t, because both of those terms go away. There's another constant function that solves the differential equation when y is -1. Because -1 squared minus 1 is still 0. At y equals -1, all the slope marks in the slope field have a slope of 0 as well. The constant function y equals -1 is a solution as well. However, that's where the almost comes into play. There's no choice for c you can make that will make this function equal -1. So it'll solve any other initial value problem, but not the initial value problem where y of 0 equals -1. If you set this equal to t equal to 0 and y equal to -1, you'll get the equation -1 equals 1. Well, okay. Maybe I should, no, it's not that simple. If you replace y with -1 and t with 0, this is what you'll get. But if you try to solve that for c, what happens? Multiply both sides by 1 minus c, you'll get -1 plus c equals 1 plus c. Cancel the c's, you get -1 equals 1, which is a contradiction. Can't happen. Assuming there is a solution leads to a contradiction, meaning there is no solution. So you can't solve that initial value problem, but you can solve all the other ones. Anyway, this slope field is constant along horizontal lines, not vertical lines. Here's what it ends up looking like. And you can see, it's not literally drawn, but it looks like it should be the case that along y equals 1, you'd have a bunch of horizontal lines, slope of 0. And yes, that does mean the constant function y equals 1 for all t is a solution. That also happens at y equals -1. The slopes of the line segments would be 0. And y equals -1 would also be a solution. Those are two very special solutions. They're called equilibrium solutions. They are functions, but they're constant functions. Their output is always the same, no matter what t is. Represents a steady state. For a population model like a logistic model, it represents the prediction that the population stays constant. How can that be? Aren't there still being bunnies born? If it's a population of bunnies? Well, yes. But when you're at the steady state, for every bunny born, there's a bunny that dies. Of course, in real life, those don't happen instantaneously. So yes, the population does go up and down a bit. But approximately, if it's a good approximation, then for every bunny born, there's a bunny that dies. What about other solutions? You got to follow the slope field. So there are solutions that look like in here that look like this, say. Follow those line segments so that when you pass through the midpoint of any one of them, it becomes a tangent line to the solution curve. Some up here. and some down here. Of course, I'm only drawing finitely many solutions. There are really infinitely many solutions. I hope it's clear looking at the picture that for an autonomous equation like this, solutions are horizontal translations of each other, not vertical translations. Yes, that's true. All the solutions in this region here are horizontal translations of each other. All the solutions in this region up here are horizontal translations of each other. And all the solutions in this region down here are horizontal translations of each other. The horizontal translation of any solution is a solution. Not all solutions are horizontal translations of each other. The ones in here are not horizontal translations of the ones down here. But the horizontal translation of any solution is another solution, because the slope field is constant along horizontal lines. With pure antiderivatives, it's constant along vertical lines. Where's the other picture? And vertical translations of solutions are solutions.